cloud, and now very much so big data going forward. So a pretty exciting area to be involved in. I'm really happy to have the opportunity to work on it, work with Michael and others here. They're also in the audience today that you can talk to and visit with. So very, very, very excited about that. So yeah, I have a trivia question for you tonight. See how up to date you guys are on this, and it's related to our topic. So if I said the following lyric, okay, into the future we must cross. We must cross. Okay. Did anybody see a movie recently that uses that theme pretty much throughout? No? Okay. Okay. So it's transcendence. Is anybody music buff at all? Yeah? Yeah, do you know what the song is? Genesis? Yeah, so pretty popular song, kind of from the 70s and 80s. Anyway, so much for my trivia question. but kind of related to your AI topic a bit later. So again, thanks for coming. With that, Michael?
Yeah. Thank you so much for Oracle for letting us have this event here. And without further ado, I'd like to introduce Michael Mozer. Michael. Thanks.
Can you find out whether that other guy is? Okay. I apparently have to wear 2 microphones because what I have to say is so important. Okay. How legible is that to folks back there? Okay. Okay. Cool. Vacuum tube. So I'm at University of Colorado. I've been at University of Colorado I was doing the calculation here a second ago. Is this cutting in and out? How about, okay. I've been at University of Colorado for 25 years, and I've always had an interest in big data, and we called it machine learning for many years, and there was a long period of time when no one else knew what machine learning was, and I asked Michael, if I use the term machine learning, are people going to know about what I'm talking about? And they looked at me like I was crazy. Of course everyone knows what machine learning is, and of course everyone's done Andrew Ng's course. It's nice to be in a community of people that have that kind of background. I did want to say a few words about the field of machine learning, because if your exposure is Andrew Ng's course, and you go to a modern machine learning conference, you'll have absolutely no clue what's going on. I've gone to the machine learning conferences since year 1, basically. They're in sort of year 25, year 30 now. And I understand about 10% of what's going on. And everyone in this room should be really scared. I am, my grad students are, because we go to these conferences and you come back feeling so stupid. Because, Kevin's laughing, he's in the front row because he goes to these conferences every year. And the field has advanced and changed so much, and there's so many really, really smart statisticians and statistical physicists and computer science theorists and optimization folks who've gotten in the act. And in some sense it's really scary. In other senses, a lot of the ideas that were around 25 years ago are now coming back into vogue, and so it's kind of like I've been around long enough that the stuff that's old is new again. But the field is really dynamic, and I just want to encourage folks not to become complacent. And if you're interested in sort of the sophisticated analytic techniques, it's really worth following the technical journals, and hopefully this new journal of yours will represent that. But the main conferences in the field, there's one called NIPS for Neural Information Processing System, and another one called ICML for International Conference on Machine Learning. Those are the meetings that, if you have a look at the proceedings of those conferences, you can get a sense of what's going on. The conferences are and each conference puts out a sort of volume. One's called NITS, N-I-T-S, for Neural Information Processing Systems. You shouldn't be thrown off by that word neural, because for a long period of time there was nothing neural in the conference, and at this point that's just a relic, but it really is the sort of most sophisticated technical machine learning conference. And the other one's called ICML, International Conference on Machine Learning, which is a bit more applied. NIPS is really the hardcore theoretician meeting. And a lot of the big advances in the field have sort of popped up at NIPS. And I have a slight bias. I'm secretary of NIPS, so I think it's a really great organization. And then journal-wise, probably the top journal is called JMLR, Journal of Machine Learning Research. The good NIPS papers end up in JMLR. So, I want to tell you today about a project that we've been working on the last couple of years, and the first author on this work is Rob Lindsay, who came down from Boulder with me. Rob just finished his Ph.D., and I'd tell you all to hire him, but he insisted, despite lots of postdoc offers, and he could have had a Google gig anywhere he wanted, he wants to stay in Boulder, and he's doing a startup, so you can ask Rob about his startup. And he has a consulting gig in the meantime as well to make some money. But Rob is really the principal on this work, and I have two other students, Brett and Mohammed, who've been involved in some of the work, and we collaborate with a fellow named Hal Pashler, who's a psychologist in San Diego, and you'll see why psychology comes into play here shortly. So I think everyone knows what A/B testing is. The basic idea, I stole a slide off the web, that the idea is basically you take web page visitors, you randomly assign them to one of two conditions, the green and the black, or the A and the B conditions. You serve up a version of the web page depending on what condition the person's in, and then you measure which condition leads to better results. This is a standard methodology. Everyone here again probably has heard about it. And what I'm going to talk about today is essentially A/B testing on steroids. So suppose we could compare not just two options or a small number of options or sequences of pairwise options, but a whole continuum of options. And I just made up some icons to represent this, that just sort of spaces of faces and cat eyes and colors and sizes of boxes. And whatever you can imagine, sort of making into this continuous set of dimensions and optimizing over those dimensions. And that's what I'll tell you about today. I'm going to go from talking about A/B testing in your universe to A/B testing in mine, because A/B testing isn't used just in marketing and high-tech companies. A/B testing is one of the core techniques of science. And in science, it's called a randomized controlled experiment or randomized controlled trial. And anyone who's taken any sort of science course knows about A/B testing. And the work I'm going to talk about today is really going to be improving on randomized controlled experiments in psychology. And what I hope you're doing while I'm giving you these examples that are really examples from psychology is you'll see the relevance to the kind of world you folks work in, and hopefully we'll have some discussion afterward about how these ideas can be transferred over. So why psychology? Well, our collaborator in San Diego is very interested in human learning and can we improve human learning. So a lot of this talk will be about how can we develop techniques that will help people learn better. And one of the phenomena we're trying to exploit, or have tried to exploit, is this phenomenon called the distributed practice effect. And you may not have heard that buzzword, but you probably have heard that spaced practice is better than massed practice. Does that sound familiar to folks? Brian's nodding his head because he's had lots of psychology. If you've taken an intro psych course, the professor will tell you it's not a good idea to cram for the exam. You want to space out your study over time and you'll do better. That actually turns out to be a lie, that if you really want to do well on the exam, you should cram for it, but you won't remember that material for very long. If you want to promote long-term retention, you should study the material at certain wider intervals of time. So that's a well-established phenomenon in psychology. And our colleague in San Diego said, well, we have a pretty good idea of how you should space material if you're going to study it twice. But now I want to study a question like, suppose you have 4 sessions in which to learn the material. How should you space the time between the sessions? So he proposed an experiment where he did a sort of equal spacing, where there was a day in between the first and the second session, a day between the second and the third, a day between the third and fourth. And he wanted to compare it to an increasing spacing condition, where there was a day between the first and the second, then 2 days between the second and the third, and 4 days between the second and the fourth. And we ran an experiment in which we had many subjects in each condition. We bring undergraduates into the lab, and they come in for this thing 4 or 5 times, and they get tested at the end, and we measure their memory based on how they've studied. And you get graphs that look like this. These are made-up graphs. I shouldn't say these are real experiment results. I wonder if there's any way to point. Do you see a pointer now? Oh, you do. Okay. So here are 2 different training conditions, or I'm going to call them training policies. Policy is just a set of procedures for establishing how you should train. And you test a bunch of undergraduates in one condition, test a bunch of undergraduates in the other condition, and you get your data points that are means with error bars, and you hope that one of the conditions gives you reliably better results. This is no news to anyone, right? This is sort of a standard experimental technique. And then you publish a paper in our case. In your case, you make money by showing there's a difference between these 2 conditions. So the problem with this is what you really want to do is not compare 111 with 124. So we got results like this, and Hal Pashler said, oh, look, increasing spacing is better than equal spacing. And I'm like, no, one particular increasing spacing condition you studied is better than one particular equal spacing condition you studied. And so what we really want to do is to find the best study schedule, the best training policy. And that may be, if you think about the x-axis of this graph as the space of all training policies, as sort of each different policy, alpha, beta, gamma for different lags, as being a point along that x-axis, there's some point there that may do better than either of the 2 that we came up with on our own. And implicit in this whole space is that there's a function that relates performance to the policy that you adopt. Right? We don't know what the blue curve looks like in reality, but it's what we're trying to discover, and what we really want to find is the peak of the function. So here's the basic approach we're going to take to do this. We're going to run little tiny experiments where we just take one subject, one student. Is subject a word people are used to hearing? In psychology, people say subjects are participants. Imagine website visitors if you want to go back to A/B testing. So we take one subject, and we pick a point in this policy space, and we test that subject, and we get a data point. And there's no error bars here, because it's just one individual's performance. They took a test at the end. They got 23 out of 25 correct. Okay? And that's really noisy, because each person is different than each other person, and one student may just happen to space out and not be paying attention. And so any individual data point is almost meaningless, and you really have to collect lots of data to trust what those data mean. But I get these 4 data points, let's say. This is still an imaginary experiment. And what I'm going to try to do is guess what that function that relates the policy to performance looks like. And so one way to do this is to use curve fitting techniques, or sometimes this is called function approximation, to estimate the shape of the function. So a really dumb technique to use would be linear regression. You say, I think there's a straight line that I can fit through the data, and you'll get something. What we do is something a little bit smarter called Gaussian process regression. And Gaussian process regression is a much more flexible family of curves. It's basically a family of curves. So linear regression gives you straight lines. Gaussian process regression gives you curves that are smooth, but that's the only constraint. And Once we've estimated the shape of this function with a certain number of data points, then we want to know what should we do next. If we have another subject coming in, where should we test them to give us information about the shape of this function? So we try to find promising points in this policy space to evaluate next. And those two green lines I drew are potential candidates because they're near where it thinks the peak are, but they aren't right at the peak. And so maybe things will be a little better near the peak. So I'm not going to tell you about the technique right now for picking those points, but part of this algorithm involves using the data you have to estimate the shape of the function. Can you hear me over the rain? Okay. And then part of the algorithm involves using the function you've estimated to guess where you should explore next. And so you only explore places that look promising. It doesn't seem worth your time to go over here and explore because there doesn't seem to be a lot going on over here. Yeah, question. I'm sorry. I should probably bring the... Is this live?
So the policy space is sort of a categorical variable, and depending on how you order it, you can get very different functions.
Yeah.
Do you have like a predetermined way of doing that?
Right. Did everyone hear his question? Okay. It's not categorical. It's actually a metric space. So we can compute distances that reflect similarity. And that's absolutely critical. You asked exactly the right question. So my example here was a really bad example because I was talking about sort of three numbers and expressing them on a line. It's really a three-dimensional space where two policies are more similar to the extent that you've chosen the same spacing between examples. I'm going to show you lots of other examples, but you're asking exactly the right question. The point is that in order for this curve to be smooth, nearby points on the curve have to result in very similar performance. And that will be the case. And that's critical to making this method work. Okay. So let me just say a little bit about Gaussian process regression. It's assuming only that the functions that you come up with are smooth, but how smooth they are is determined by the data. So there's free parameters that determine the smoothness, and you let the data tell you that. It's very efficient in the way it uses data. With relatively little data, you can get good curve fits. And that's Gaussian processes are a Bayesian method, a non-parametric Bayesian method, and the strength of Bayesian methods is that they do reasonable things with little data if you start off with the right assumptions to begin with. And the assumption we're building in is this assumption that the curves are smooth. And it will produce estimates both of the shape of the function and how much uncertainty it has in its estimates. And I'll show you that here in a second. So I'm going to start with a simulated experiment. This is all inside the computer where I made this function by hand. I think I made this one, right, Rob? You wouldn't have done something dopey like this. So this is the real function. The system is going to try to find this peak without knowing the shape of the function. And it will start off by running a few subjects and getting data from them. And this is all in simulation. So to get simulated data, what I do is if the algorithm says, I want to test at this point in policy space, the mean performance will be here, but any individual varies a little bit, so I add noise to it. And that's a sample that this individual got 7 out of 10 correct on the test. Okay? And we take these data points, we do function estimation. It's not very interesting so far. So this is the Gaussian process posterior. It's best guess about the shape of this function. And the Gaussian process gives us not only that estimate, but it gives us uncertainty. And I'm going to reflect that in color. Pretty picture. So this is a cumulative density function, but basically the intuition is the further apart the red and the blue areas are, the less certain it is that this is the correct function. I set it off. All right, so now it's running the simulation, and it's adding 5 subjects at a time. The dashed line is its estimate of the function. The solid line is the actual function. And you can see that very quickly it's picked up on where the peak of that function is. Each of these little dots is an individual subject or a small number of subjects that it's tested. So here it's ran 100 subjects, and it ends up picking as its peak the same point, which is the true peak of this function. It doesn't have a really good idea what's going on over here where the policies don't do well, or over here where the policies don't do well, and it didn't really get this little peak, but none of that matters, right? Because our goal is only to find the very best solution. Does this make sense to everyone? Okay, so now you have an intuition for what's going on. Here's Rob's math. And I'll blow up a little bit of this math on one slide. It's only slide with math, and this is sort of statistical jargon on the slide. So incorporated into the way this whole thing works is some model of how people behave, how people respond to a policy, how they learn, how they perform when they've learned a certain extent. So we're going to say that each policy, which is going to be this vector x, results in a certain skill level, which will be that function value. So the function we've been, well, no. The underlying function is representing skill level. And that's a draw, this is statistics jargon to say it's a draw from a Gaussian process with a certain mean and a certain covariance matrix. That function is going to range from minus infinity to plus infinity. The function is unbounded. I promise there's only one page of this. You can ignore me if it isn't making any sense. And what we really want to do is get numbers that people produce. So we want something much more like what's the probability that someone under a particular policy will be correct. And so we can do a transform of this minus infinity to plus infinity to a 0 to 1 value that represents the population accuracy. And then we want to model how much individuals differ from one another from the population. And so we have a model of individual differences. And this is the average percent correct for an individual, but now they're taking a test with a fixed number of items on the test. So if there's 25 items, they're going to get between 0 and 25 correct. And so we need to model the probabilistic draws of the exam score that a particular student gets. So you put these whole things together, and this is sitting on top of the Gaussian process. So the Gaussian process represents this family of possible functions, and then we transform that function into something that we observe, which is the number corrective a particular student gets. And this all has a fancy, here's a fancy graphical model picture that Rob made, and Rob tells me this is called a chance-corrected beta binomial observation model. See, I'm blaming you for the jargon. Okay? This model has a couple free parameters. It has parameters of this covariance matrix. It has parameters of individual differences. And we use the data to fit those free parameters. But it's really remarkable. The number of free parameters in this model is very small. So almost all the constraint comes from very little data. And the model makes some very strong inferences that result from these free parameters that are fit. Okay? And the particular way we fit them is with hierarchical Bayesian inference, but you can do maximum likelihood fitting or least squares fitting. It's all pretty much the same. So now I'm going to tell you about how we've applied this to a couple of problems in psychology. So these are real experiments with real people. And this is an experiment where we wanted to teach people some facts, and we're going to show them a bunch of pictures of people, and we show them the name of this individual's favorite sports team. I don't know if you can read the blue bar, but it says Jets fan. So each individual we're going to show them is either a fan of the Sharks or the Jets. I picked Sharks and Jets from West Side Story, but I guess they're actual sports teams, right? So we're going to train them on 6 faces at once, and we're going to train them for 30 seconds. And we're going to show each face for a duration, D, which we're going to try to determine what the best duration is. And because there's 6 faces and 30 seconds of training, each face will be shown for 5,000 over D times, if D is expressed in milliseconds. Okay? So if we show each face for a duration of 5,000 milliseconds, then 6 faces will take up 30 seconds. Each face will be shown once. If we show for a duration 250 milliseconds, then each face will be shown 20 times. So after they've been trained, we show them both of the alternatives, and they're tested. They have to pick whether they think this person was a Jets fan or a Sharks fan. And Rob set up a demo for me, and should I trust it's going to work? I actually tested it this morning. Okay, so here's the actual experiment, but oh, why isn't it no to just use... Alright, this may not work. So, here you're being trained for 200 milliseconds a face, 250 milliseconds a face. There's 6 faces here that's showing over and over again. We're on 30 seconds. Is it ever going to end? This is the longest 30 seconds of my life. Okay. All right. Rob makes these really sexy websites. Look at this. Countdown. All right. So then I have to choose. Did I think that... does anyone know? Is this person... Sharks? Okay. It's not giving us feedback, but we're going to make the choice. Okay. Jets? I think there's a balanced number, so there must be some more sharks, right? Oh, look at that! You guys did good. Is that demo always the same? Okay. All right, I won't do the 5-second demo, but the 5-second demo, you see each face for 5 seconds, and you see 6 faces just one time. So what we have is this continuum from that very short duration to a much longer duration. At the short duration, you see each face 20 times. At the long duration, you see each face once. And to some extent, more presentations is better, but there's diminishing returns with the number of presentations. And to some extent, more time to process each face is better, but there's diminishing returns. So there's going to be this kind of trade-off between, short but many and long but few. And what we're trying to do is figure out what value of D gives us the best results. How many times should we show each face? So we did this with 8 blocks of training and testing. There's 6 faces in each block. We run all our experiments on Mechanical Turk. Everyone knows Mechanical Turk, right? And we paid subjects 30 cents. They've gotten more pissy with us, so we have to pay them more than 30 cents these days. So here's the actual experiment running. So each one of these dots now is a new subject, and the x-axis here is the duration, and it's plotted on the log scale, just because for the short duration, the small differences are more meaningful than the long duration. And then the y-axis is accuracy on this final test on average. And so we're up to 50 subjects. It's going to go up to 100, I think. But you can see it's found what it thinks is the peak right around here, which is like 1150 milliseconds. And one thing this model does is it does a lot of smoothing. You can see how noisy the individual data points are. And to the extent the data points are very noisy, you get a kind of regression to the mean. So the curve doesn't look as impressive as it probably is, because it's being conservative about where it thinks the peaks are and stuff. So you can see that it has still a fair amount of uncertainty. If you think about this region, say, between the blue and the red is the region of uncertainty, the function could very well start down here and go all the way up to here and go back down. So it doesn't have a lot of confidence about the exact shape, but it does have a lot of confidence about where the peak is. Is there a question? That's a good question, right? So the question is, if we threw the outlier, if we said, okay, we don't think this region on the right is very interesting or this region on the left is very interesting. Let's just focus on the central region where we get a better result. And my gut intuition is no, because the one thing this technique is doing really well is it's using like a subject over here because of the smoothness constraint. It's using it to make constraints on the whole function in this neighborhood. So each data point is helping constrain the local neighborhood, and all these local neighborhoods connect to each other. So my intuition is that you actually get benefit from that. One thing we should be doing that we haven't really done yet is running more replications, where we just start the experiment over, use a narrower range or a wider range, just to show that you get the same result. Yeah. The question is, why is this difference so kind of piddly, right, between 80 and 85? And again, I think it's this regression to the mean effect where it's just being more conservative. It's assuming there's more smoothing than there probably is because the data is so noisy, and you'd need lots of data to... If I kept running this for another couple hundred subjects, you would see it start to peak more. Okay. So it does this very efficiently. So I have on the x-axis the model's belief about what the best duration is as a function of which trial, which subject I'm running. And you can see that, and this dashed line in the middle is where it ends up after 100 subjects. And you can see that after about 45 subjects, it's gotten into the right neighborhood for that peak. It's jittering around a little bit, but it's basically found the solution. So that's a very small experiment by psychology standards with 40 or 45 subjects. So Rob decided to run a comparison with a traditional experiment where he said, I'm going to test 5 different conditions. This is the condition where you show each face 5 times for 1 second, and this is each face 1 time for 5 seconds, and this is 4 seconds, 3 seconds, 2 seconds per face. And he ran, because we ran 100 subjects in this other experiment, we ran 100 subjects in this experiment, so there's 20 data points in each of these dots with error bars. And just looking at this, you kind of get a general sense of the shape of the curve, so it's validation, but there's this noisy point which happens to be, fortunately for us, right where the peak is. So I'm going to superimpose the results of this experiment with our original experiment. Right? You can see that the 2 experiments are roughly consistent with one another, but I would argue that our pretty curve is a lot more interpretable. It's a lot easier to see what's going on if you buy into it in this other experiment. Right? You'd be hard-pressed to pick this as the peak if you saw this data point, which is how it turned out. So everyone's on board? Is anyone bored? Bored? I'm going to do one more psychology experiment and then some stuff that probably better connects to things people would find relevant to the real world. What time are we trying to finish by? Oh, I'm doing fine. Okay. So this is going to be a concept learning experiment. So this other experiment was learning facts, kind of rote memorization, not very interesting. And psychologists are much more interested in teaching you new concepts. And here are the instructions for the experiment, which you can't see, which say basically, imagine an alien from this Andromeda galaxy comes to teach you their language, and they want to teach you their concept of Glopnor. And they're going to teach you by example where you see objects, some of which are Glopnor and some of which aren't Glopnor. So it's like a kid learning the first words of their language, or you going to a foreign country and trying to infer a word, or starting at a new company and they use some technical jargon you have to kind of figure out along the way because you're embarrassed to ask them what the jargon means. Right? So here's how the experiment starts. You see a picture of an object, grapes, and you're asked, is this Glopnor? What do you guys think? That was a silly question. Okay, so suppose you said, perhaps no. And it says, wrong, this is Glopnor. And then you see in the next object, and it's showing you the previous object in its class, just so you can be reminded. And here's a camel. Is it Glopnor? And this one I said no. And it says, correct, this is not Glopnor. And it keeps going on. So now here's a clothespin, and you have to categorize clothespins. And you do a bunch of trials like this, and then you get tested on objects, and you're asked to say whether they're glottal or not. Turns out subjects really enjoyed doing this experiment. I'll actually come back to that later, because it inspired yet another experiment to take advantage of Turkers. So unbeknownst to the subjects, glottal just means how graspable is an object. How easy is it to pick up and manipulate with one hand? So these psychologists did a norming study where they went out and asked people on a 1 to 5 scale, how graspable is a building or a roulette wheel or a horse or a toothbrush? And obviously, toothbrushes are very graspable and buildings are very not graspable. So we had these numeric ratings. It's a continuum from 1 to 5. And we just said, we're going to define an arbitrary boundary at 2.5. Anything to the right of it is glottal, anything to the left of it is not glottal. Okay? So now we want to talk about the manipulation we're doing to help people learn. And the first manipulation is called fading. It's this idea that's been around in psychology since the days of running rats in labs, that if you start with easy examples and make them harder over time, you can kind of wean people into it's the opposite of weaning them off, right? You should sort of lead them into understanding the category. So here's a representation of that. So if we have 25 training trials, and this y-axis here represents how far is the example from the category boundary, from far away to near the boundary on that rating scale. So examples that are far away are things like the toothbrush in the building. And if I just show you toothbrushes in buildings, it's going to be pretty easy to figure out, it's something small and large, or you'll get some idea of what it is right away. On the other hand, near the boundary are really messy things like frogs, which kind of are graspable, but they slip out of your hand. And so the examples near the boundary are hard, and the ones far away are easy. So what a fading strategy is to move from far to near over time, and psychologists have compared this sort of fading to a case where, say, you just show them easy examples or just show them hard examples. But what we've done now is to say there's a whole continuum of possibilities. Each one of these lines is a different fading schedule, a different schedule for how the examples become more difficult over time. And so we really have this continuum from start far, end far, to start near, end near. And so this is going to be one of the dimensions of our policy space that we manipulate. The other one is another issue that psychologists have looked at and been interested for a long time, which is blocking versus interleaving. So blocking is the idea, if you're trying to teach people a concept, you want to show them many examples of the same category before switching to the other category, because then you can see the similarity between examples of the same category. Whereas interleaving, the argument is, if you see contrasting examples, this is glottal, this isn't glottal, you'll get a much better idea about what makes the two different from one another. So there are arguments in the literature about, blocking is better, interleaving is better, whatever. Let me just say, a way of characterizing these two strategies is that blocking involves, from trial to trial, mostly having repetitions, and interleaving involves mostly alternating between the categories. And so I'm going to turn this mostly repetitions, mostly alternations into a continuum by characterizing how each trial is in terms of the probability that it's a repetition of the previous trial. So if we have a function that looks like this, we start off with high repetition probability, so we start off with blocking, and at the end we have a low repetition probability, so we end up with interleaving. So this is a block early, interleave late strategy. We can flip this around as interleave early, block late strategy, or we can have a strategy that just says the repetition probability is 0.5. There's sort of no structure to the sequences. They're just random sequences. Did I go away? And then there's everything in between. So this is our second dimension. So we're going to specify a policy as a point in this fading space, a point in the blocking interleaving space, and we'll then generate a sequence of 25 training trials from that policy, and we run the subject, and then we give them 24 test trials, and they don't get any feedback. They have to make a choice, and these subjects got paid a quarter. And here's the result. So this axis is the fading policy. from all easy to all hard to fading in between. And this axis is the blocking policy from alternating to block to alternating. And the dots are subjects we've run in this space. The bigger the dot, the more subjects we run in that condition. And then the contour map tells us what the accuracy is on the final test. And so the optimum in this space is a point right around here. It's a point that, no, I didn't put this on the slide, where the fading policy starts from an easy case and goes to a semi-difficult case, but doesn't go to the really difficult cases. And I think the reason for that is the really difficult cases are things like frogs that are just too ambiguous, or birds that, in principle you can grab it, but it's not going to let you grab it. So it decided an intermediate level of difficulty was best, and it decided that you should start by repeating examples from the same category initially, and then later on alternating examples between categories. Okay? So we can stand up and say, here's our result, believe it, this is just Bayesian inference, and Bayesian inference is doing the right thing. But unfortunately, that isn't enough to convince the world. So you have to run a more traditional experiment to compare against. So we ran an experiment where we tested a bunch of subjects in each of these corners in the center of the policy space, as well as at our optimum. And the optimum did come out better than any of the other points. But it turns out the experiment's so noisy that these differences aren't statistically reliable. And Rob and I finally decided we don't want to run 500 subjects at each point to get a statistically reliable difference. But in any case, this more traditional comparison came out in our favor. Any comments or questions about these training studies? Because I'm going to move on to things other than psychology and training studies. So we have a couple collaborations that are pretty new collaborations, but I just wanted to tell you about sort of where we're going with this work. And one of these has to do with color aesthetics. So we have a friend named Karen Schloss who's at Brown University, and she studies how people perceive colors and their combination, and how experience shapes your preferences, like what school you went to affects your favorite colors, believe it or not, and how preferences influence cognition and decision making. So she can, if she gives people red and blue M&Ms, she finds that Democrats tend to choose whatever the Democrat color is, and Republicans tend to choose whatever Republican color is, but it's only contingent on them being thinking about elections. So the week before the election you get the effects, the week after you don't. So she does all these cool things, and she does a lot of website design too, like sort of what's the right layout that is how do you take advantage of perceptual grouping cues. So one of the studies she's done is of color preferences, where she shows people a huge variety of pairs of colors with a figure, the sort of small square, inside a background, or a ground, the larger square. So this is blue as figure and pink as background, or light green as figure and red as background. And she asked people to rate these objects, the color pairs, on a number of dimensions. The one I'm going to talk about is just how much do you like this? How well do these colors go together? And she gives them a little slider on the computer screen, so they aren't giving you a numeric value, they're just picking a point on the slider. Okay? She did this with 48 participants. She, obviously you can't do every possible color combination, but she picked 32 colors that represent sort of a variety of saturations and hues and intensities. And she paired each one of these 32 colors with every other color except for itself, so that you have a contrast between the figure and the background. So that's 31 times 32 color pairs, or 992 pairs that subjects had to rate. So then she sent the data to Rob. So Rob got 992 times 48 numbers, and it was Rob's job to make some sense of it. But before I show you that result, let me show you the results in her paper. So I mentioned she had subjects rate these on a couple dimensions. This dimension is going to be the dimension of how much do you like this color pairing. So ignore the way things are spread out along here. That's irrelevant. But the things down here are color pairs that people didn't particularly like, and the things up here are color pairs that people did like. And this is all 992 pairs. It's a big mess, and you can't see most of them. So here's another way that Rob came up with visualizing what's going on. Rob said, let me, based on the hue of the ground and the saturation level of the ground, how dark to light it is, let me take each of the ground colors that Karen studied and show that ground color along with the figure that people liked best to go with it. So this is the, are you seeing the colors well enough? Okay. These are color pairs that people found to be nice together. And the points are kind of all scattered in a weird way around this space, and it's because when real color perception experts study color, they don't use a hue, saturation, intensity space or an RGB space like all of us think about, because we think RGB is what represents colors. It turns out there's this other space. Does anyone know about color? There's this thing called CIE lab that represents a spectrum of colors that you can't even represent on your monitor, but that people can perceive. I didn't know this. There's colors out there that you can't generate on your computer monitor. So they have this really fancy monitor that generates colors in CIE lab space, and that's the space she's actually exploring. And when you map it to hue, saturation, intensity space, it looks kind of dorky the way it's laid out here. Okay? So these are the most preferred pairings, and then here's the least preferred pairings, and you can kind of see that there's these ugly combinations like red and green together that just kind of make you want to get away from it. And so these are the data that Karen gave Rob to play with, and Rob said, let's try fitting our Gaussian process to these data. And so now fitting the Gaussian process, each color, each foreground color is a, what are the LAB spaces? An L and an A and a B value, whatever they represent. It's a triple, like RGB or hue, saturation, intensity. And so we have 3 of those values for the figure, 3 for the background, so it's a 6-dimensional space. The nice thing about the CIE lab space is that the distance between points in the CIE lab space corresponds to human perceptual distance. So if you ask people how similar are these 2 colors, the distance in CIE lab space will predict their response. And so that's a very nice space to respond to the earlier question, because now we know points that are nearby in this space are going to be points where both the figure and the ground are very similar perceptually, and so people should presumably give similar ratings. So we have a reason to expect that our function that maps color pairs to ratings is going to be very smooth. So here's what the results look like, and it's fun to look at. And Karen's looked at this a bit, and Karen likes, she can come up with interpretations of why it's chosen what it's chosen. Like she particularly likes this little region, which is black on top of orange. And she's like, oh, that's a familiarity effect, that's Halloween. But who knows if that's right. And these just happen to be the color pairings that the model thinks are the very best. There may be other pairings that are almost as good, which explains why there's this kind of discreteness to the space. But again, the cool thing is, Rob has taken the data that looked like this and mapped it to data that looks like this, and has extrapolated sort of way outside the region that Karen provided data. And then here's the least preferred. There's a lot of puke green there, right? Karen says that's because people associate it with vomit or feces or whatever. Okay, do people want to look at this anymore? So let's move on to a different project that takes advantage of this idea, and it has to do with charitable giving. So if you open a mail solicitation, like in your physical mail, if anyone still reads physical mail, or you go to a nonprofit's website, you'll see something like this. This is the CU Foundation site. I just pulled it off the web right before I came here, and I knew it would have what I wanted, which is this little region here, where they ask you, I can't read it on my version, but they ask you something like, how much would you like to donate? And then there's options like $5,000, $1,000, $500, $100, $50, or you can fill in your own choice. And the reason why they do this, everyone can intuit it, but there's actually a field of psychology interested in this, a field called anchoring effects or cognitive biases that says the choices you're given here, even if you fill in the number yourself, the choices you're given will affect what donation you make. Like if you were to donate $1 at this point, you'd feel really cheap, right? On the other hand, if the choices were $1, $2, $3, $4, $5, you wouldn't feel cheap. So, and there's also strategy to the fact that the box is up here, and this is a nice progression from small values to large values, right? So it looks like, oh, I better put a really large value up there. So they're pretty smart about this, but Rob and I asked whether we could be smarter still. And so we did a Turk experiment where we tried to optimize these anchors. The anchors are these numbers that you're given as suggested donation. So we had our Turk participants do a bogus task. I don't even know what it was at this point. Just like check some boxes. And we paid them a nickel. And then they get taken to a page that's a donation page where they see, this was right after Hurricane Haiyan, what was it called? Haiyan in the Philippines. And they see a couple pictures from that horrible tragedy, and they're told, we're going to give you a 10-cent bonus for doing our experiment. And if you want, you can donate some or all of this bonus to the Red Cross for disaster relief. How much would you like to donate? And then we have a couple choices that we picked from our model, and then a fill in the blank. And they can either check off one of the predetermined donation amounts, or they can type in their own response. And so what we want to do is optimize this triple of anchors. So there's this ABC triple, and because we're giving them a dime bonus, and there's no way with Turk that we can take more money from them than we've given them, all we can do is remove their bonus. So we're limited by how much we can ask them to give. So they can give between 1 and 10 cents, and we've ordered these ABC values, so B will always be bigger than A, and C will always be bigger than B. Okay? So this is a space of possibilities. You know the exact number of these things? 10 times, it's sort of 10 times 9, it's a couple hundred, right? 500 maybe possibilities. I had to write a little program to actually loop through because I couldn't do the actual math, but I've forgotten what the number is. Anyhow, this is the result of the experiment, and so now we're trying to visualize a 3D space that has the A value, B value, C value. So each one of these rectangles is a C value. So this is if C equals 3, C equals 4, C equals 5, up to C equals 10. And then the x-axis is the A value, and the y-axis is the B value. And these constraints among the values are why you see these little triangles, right? Because if the biggest donation amount is 3 cents, the only other values you can ask people is 1 and 2 for A and B. On the other hand, if the biggest value is 10 cents, then you can take any combination of A and B values up to, but not including 10 cents. Okay? And the coloring represents how much the Turk subjects gave. This is, I can't read it, 6 cents at the top and 3.5 cents on the bottom. So people are actually being very generous, and there's big differences in these effects. And the disappointment to Rob and I is that the optimum was in this upper right corner, this maximum. So if you give them anchors that are the maximum values, they give the maximum donation. Nice in the sense that this phenomenon is well known, and we've verified that we can discover that from the data. It's not so nice because it's the best solution is in a corner, and you want the best solution to be somewhere more interesting. So we're starting a new experiment, and we don't have results for it yet. And I'll just tell you about the experiment because I'm kind of pleased with how clever this is in terms of coming up with a way to avoid this cap at 10 cents. So we give people a boring task, and we tell them to do this for 20 trials. And the task is actually, I'm going to show you the letter F or J, and if it's F, hit the F key, and if it's J, hit the J key. So you just see F, J, J, F, F, J. We do actual experiments with this where subjects have to do this for 2 hours. It's really torturous. And then they have to wear an EEG skull cap while they do it. And you have to stop every 100 trials and re-oil the skull cap. So we've done worse things to people. So then we give them the option to donate more time. We tell them, okay, you've done our task, you've earned 5 cents or whatever. We can't pay you anymore, but for every additional 20 trials you pledge to do, we'll donate 1 cent to the Red Cross for disaster relief. And if you don't complete your pledge, we won't donate. So they can't just make a pie-in-the-sky promise. They actually have to follow through, and they do more trials. So if they donate a penny, they have to do 20 more trials. If they donate 10 cents, they have to do 200 more trials. And then it's all the same. And the only difference now is that there's no need for us to cap this at 10 cents. And we think this is going to get much more interesting results. Because if we give you anchors like 1,000 cents, well, 1,000 cents is 20,000 trials you're committing to. No one's going to pay attention to the anchors. So there's going to be anchors that are just too large to convince people to adopt or to pledge their time. And if it's too small, then we know that they'll go along with the small donations. So we think we'll find a peak in this function, and I think you're halfway through this and you are starting to see that peak. Oh, okay. We've run into technical troubles, Rob. Rob, by the way, finished his Ph.D. He's done like 4 Ph.D.s all rolled into one. This is just a tiny part of his thesis. And because he's staying in Boulder, he's still my graduate student forever. It's even worse. He's working for my brother's company part-time. I'm not letting him out of my clutches. All right, here's one last project I'll tell you about. I have till 7:45. Is that right? Okay, my clock says 7:30. And this is with Ring N, and I'm not Chinese, so I don't know why Yun N is pronounced Ring N, but it is. And he's at University of Washington. And he works with a group that develops computer games, and mostly what they do is educational games. And the particular game that we've been playing with is this thing called Tree Frog Treasure. And I don't really, I'm inferring what the game is about from looking at this screen. So there's a little tree frog, and he has to decide how high to hop. And he's told, and you can't really see it here, or I can't see it, but he's given a fraction, like 2/6. And so he's told, I want you to hop 2/6 of the way. And there's 6 little markers here, 1, 2, 3, 4, 5, 6. And there's also a pi representation of the fraction. So here's 6, 6, and here's 4, 6, and here's 0, 6. And so he's given this numerical fraction, and he's given some hints with the pi fractions, and he has to pick a point along here to jump to. So it's basically a fraction game, and they've cast it in terms of hopping frogs, and maybe if the kids are the right age, they actually care about the stupid frogs. And blue walls are slippery, so if you jump too high or too low, I think you hit a blue wall. So they're trying to solve these number line problems and learn fractions. And the way they designed this game, there's many variants of the game, many configurations. And there were 4 different design decisions they made. 3 of them were binary and 1 was 4-way. And so any subject who comes into their experiment will get one of these configurations. And they ran some huge number of subjects. Here it is. Like 360,000 trials altogether. The students are using this in a school, so they're able to collect a lot of data. And each student is randomly assigned to one of these configurations. Not quite true, but close enough. And they're interested in which of these configurations are more or less likely to cause the students to quit playing. And so we want to know sort of what's going to engage the students, what will keep them going, what will discourage them and make them stop. And so here's results. And I'm not going to try to explain what these cubes are, but there's 8 cubes, and each cube has 8 points on it. And so there's 64 points on the graph. And those 64 points correspond to the 2 times 2 times 2 times 4 configurations, okay? And they're laid out in a space where the distances, like these 2 points, are more similar conditions to one another than this point and this point, okay? We don't have to understand exactly what the conditions are, but there are things like you see a pie chart versus a fraction, or you see some animation or no animation. And I can't remember what all the other, how many hints do you get, that kind of thing. So here's the empirical data, and you can look at it and you get a little bit out of it, like whatever this top row of cubes is better than whatever the bottom row of cubes is. Oh, sorry, it's the other way around. The bottom row is better because the bottom row has more yellow, and the yellow means higher more engaging, more likelihood that the student will continue on with the game. We also have a graph like this, not for engagement or persistence, but rather for performance. And so here's what comes out of the model when we run the model. And you can see the model's done a lot of smoothing, so a lot of these differences the model has decided are noise. And what you do see is as you go from right to left along whatever this dimension is, things get better. You definitely see it both above and below. You don't see a lot of differences within the cube. And whatever the bottom row is much better than the top row. And so I would argue that this model interpretation of the data is a lot more interesting than the empirical data itself. So the smoothing that the model does buys us something. What we haven't tried to do here or with the color experiment is to ask, can we get the same result with far fewer subjects? So we used all 360,000 trials to get this result. And the next thing we're going to do is to run experiments where we have this big database of results from subjects, and we can query that database to give us subjects to simulate running experiments. And my suspicion is we'll do it with far, far fewer subjects, but we haven't done that yet. So I don't want to speak French because I can't speak French. Coup de grace, is that right, French? I don't even know what it means. I used to speak French fluently, believe it or not. I grew up in France. But we're going to do this in a different game setting. We want to play with Flappy Birds. So Rob and Mohammed Kaja have made an implementation of Flappy Birds where there's many knobs you can turn. Everyone probably knows Flappy Birds, right? You try to make, you push a button to make your little bird flap, which makes it go up, and it moves from left to right, and it has to dodge hitting these pipes. And it has to fly in between the pipes, and it's impossible, and it's really frustrating. And you can manipulate things like what's the gap between pipes, and how far are the pipes apart, and how strongly does gravity pull the bird down, and how strong are its wings, so every time it flaps it goes up. And I think there's one more parameter I couldn't remember. And so now we have this space of policies, and we want to ask what's going to make the game more fun for, let's say, naive subjects. And we have a neat way of testing this, and the inspiration for this came from that concept learning experiment I told you about, where after subjects did the Glockner study, I got a bunch of emails from subjects.
run 100,000 students to find the optimum. If you run 20,000, then that other 80,000 students are all going to benefit from learning. Likewise, you're trying to figure out what's going to give me the best click-through, and yeah, you could do A/B testing and run 100,000 web visitors, but if you ran 20,000 web visitors or 10,000 and got the same result, then that other 90,000 would be performing, taking advantage of that optimization. We can always make up more complex configurations or dimensions. So we can easily think of things like angry birds that are 5 or 6 dimensional spaces. And even when you get large number of subjects, running any sort of grid search in these high dimensional spaces, you face a cursive dimensionality. And we think we can get around that cursive dimensionality. And the last thing that I find most interesting is the experiments I showed you about are tuning to populations. And you're using all the data from all people to tune, for the whole population. But what we really like to do is tune to individuals. We'd either like to learn rules that are based on the individual, or just learn what's optimal for an individual. So I'll give you a little bit of a flavor of how we can do that. Rob sent me an email yesterday saying he decided he was going to do the color optimization experiment with just individuals. So each individual is given us 992 ratings. And Rob asked the very simple question, how many ratings might we need to collect from an individual before I'm very confident about where that individual's peak is? And the answer is 75. And that's actually a very pessimistic answer, because it's not taking advantage of any of the knowledge from any of the other individuals. It's saying each individual is totally distinct from each other individual. And I'm not correct. So it's not exploiting background knowledge, it's not building into the priors of what we believe in other individuals. So if my color preferences were totally opposite of yours, it would be just as good at either one of those. And so that's pretty amazing. 75-ish trials to find the peak, as opposed to the 992 combinations. And so I think that, thank you.
Towards like a real-time optimization of the algorithm so that the game actually changes shape to be more engaging and...
Yeah. So there's a question of sort of what the turnaround time is like. How quickly can you use an individual's data to update a bit of a bottleneck. So if we're doing individual optimization, the Gaussian processes are very expensive to run. Actually, running the Gaussian process itself is pretty efficient. It's an order of a few grand is the number of data points. But is that right, Rob?
I think so.
You get a problem that it's really big, but there are ways around that. But the real catch is the Gaussian process represents this function value. It's not what you're observing, it's something like skill level. And you have to map out what you observe. And the only way to do that is through Monte Carlo sampling. And so for almost all of our domains. And so it becomes very expensive to do that sampling. So what would you guess, Rob, if you have a couple hundred subjects, how long does it take to sort of take those couple hundred data points and make a prediction for the next one?
I mean, it depends entirely on exactly how that mapping goes forward. I mean, it's, you know, you can simplify the mapping process to make that few hundred subjects. But if you use my code, it's going to take a few minutes.
Yeah, so that's a battle for us right now. And I'm just finishing a grant proposal to continue this
Well, a few minutes is not too bad if they're engaged for that period of time.
Yeah.
You have time to move while they're still there.
I want to advertise this as something that sort of instantaneously happens. And there may be more heuristic techniques, like you could just do some sort of polynomial function fitting, and maybe that's good enough. Or some nonlinear regression or neural net. Maybe that works and you can train neural net really quickly. So I don't think this is the only way to go. The really nice thing about the Bayesian approach is that you get this measure of uncertainty, and having that measure of uncertainty gives you a lot of information about what to test next, because you could go to regions of the space where you're not very confident that you know the value, or you could go to regions of the space where you think things are going to be pretty good. And what we use is a measure that combines the two of those, that says, let's take your guess about the mean and say, suppose we're being pessimistic and things are actually at the upper bound of our uncertainty. And would this be a good place to go if that was the case? So it depends in part on the uncertainty and in part on the estimate of the mean. And so having that uncertainty helps it explore very efficiently. And if we use these other techniques that don't give us that uncertainty, we lose that. And so I don't know what the hit would be in terms of efficiency of the algorithm. Yeah.
With this Turk subjects design, do you have a way of controlling confounding variables like socioeconomic status or age?
Yeah, it's about the most uncontrolled of experiments you can run. Rob has done smart things like check to see whether the web browser is defocused, like when people just go away, and he has to do checking to see how people just hang finger one finger, finger one finger. So we do some sort of basic reality checking to make sure they're paying attention. And for the most part, I'm impressed that we can use the data without a lot of cleaning, but they're much more varied subject pool. We get in the US and the US and varied ages than any laboratory experiment. At this point in psychology, the psychologists have kind of bought into Turk. And so people do in-lab studies with undergraduates and compare it to Turk results. And there's been pretty good agreement, which is amazing, considering. And everyone agrees that the data is a bit noisier than in the lab, but that's like it. And it's nice because you can really generalize your results outside of this 18 to 22-year-old population of college men. Rob actually ran two versions of the donation experiment, one with just US citizens and one with non-US citizens. And what's your bet on how it came out?
Which experiment?
The donation, where you're asking back some of your donation.
Who's more generous?
What's that?
I'm just commenting. Who's more generous? I don't know.
Yeah, well, that's a good question. Who's more generous? Yeah, it was just the opposite. The non-US were more generous. So. And they're all the only reason why non-US citizens would be different a priori is they're paid still in US cents, and US cents may not have the same meaning to them. But these are all people who do Turk a lot, and So they're used to getting paid in dollars and cents. Yeah.
So for a lot of the things when you were doing the experiments over time, and you had like the clustering and also the fading, all those paths that you showed through that space were all linear. Have you thought of doing any nonlinear or disjointed?
Yeah. So the question is, why you didn't fade, why didn't you just do those straight lines? And another question you could ask is, why is it just a function of time and not performance? Maybe you want to get harder when they're getting the answers right, if they're doing well. And those are all good questions. And we have another grant in that's specifically to study concept learning that's going to explore all those kinds of things. And that's the ultimate goal. This was just a demonstration experiment to show that the scheme would work in principle. And it's already a lot more general than most of the experiments that have been done. I mean, most of the experiments that have been done compare to those straight lines. Right.
Your donation one would be interesting, I think, to do an experiment where it uses the queuing. So there's been studies where, say, 10% of people donate this much money, and people are change what they do, and then another dimension to see where you end up maximizing.
Yeah, so Brian suggested, well, if you say other people like you gave this much, maybe that would serve as a spark. We've also talked about using different pictures that will yield the most donations. Like what's a really sad picture or a happy picture. I should probably stop.
Probably. Any more?
I have one question.
Go ahead, Gary.
The curves and the charts that you've provided based on the information that was collected during the experiments seem to be create its own narrative surrounding the information and how that information should be interpreted. How well does that narrative fit the outcome and the goal of the experiment? Are the narratives and the algorithms selected to meet the goals of the experiment, or are the goals of the experiment somehow created objectively from the algorithms?
Well, the experiments we set up without knowing what the outcome was going to be, but we had some intuition, like the donation experiment. We expected the anchoring would have an effect on performance and that bigger anchors would help them. You're absolutely right that what you see coming out of the model is an interpretation of the data, not the raw data at all. You say the narrative, that's more elegant way of saying it than an interpretation. And to the extent we're able to verify, the verification is matched our narrative, and to the extent that experts like Karen can look at these results, and she can come up with a story, although people are really good at coming up with stories about whatever data they end up with, right? So we need to do more work. I think the most critical thing we need to do are replication studies to show that if we run this experiment over and over again, it always gives us the same result. And when we combine data from lots of experiments, we get some sort of ground truth that we can compare against our model. So we're not quite there yet. We tried to do some of that stuff I told you about. It's actually, each of the results we've gotten, after the fact, we found some literature that was consistent with that. So the particular blocking and then blocking early and interleaving late, which was that one dimension. It turns out there's a paper that argues for that. There's probably a paper that argues for just the opposite, but at least it's a plausible theory in psychology, right? And the last thing is a good question to ask an experimentalist is, how many experiments did you run and you didn't tell us about? Right? Because we could have run 50 experiments and only the ones that seem to work really well. And you've actually seen everything we've done that didn't have a bug in the code. In fact, that fading experiment had a bug in the code, and so the first 50 subjects or so it ran in that lower left corner of the space that we're pretty much missing.
Yeah, but you understand my point that it's the algorithms that actually shape the information, that create the narrative, that help.
That's absolutely right. Yeah, the algorithms produce an interpretation of the data, but a statistical test is also an interpretation.